Worksheet 2B also apply the concept of the design and analysis. And in this case, the steel lap joint is held together by one bolt. The failure shear stress. So in this case, they talk about shear stress. The failure. So the failure shear stress. So in that case, as you can see, this equal to 30 KSI. That is the shear stress. Do you recall what is the shear stress stand for? Tau shear stress. And in this case, fail. Tau fail. Determine the required bolt diameter that the bolt include in there. To the nearest 1/4 an inch using the factor of safety is 2.5. That's a factor of safety. What is the actual factor of safety for the bolt you choose? So after you choose the actual bolt, go back to check what is the factor of safety, and it should have to be greater than or equal to the original factor of safety 2.5, because if less than, then you don't meet the design requirement. So anyone remember what this problem is come from? Is that finger is familiar with you? To do that, let me go back to the worksheet 1E. In lesson 1, we had internal shear force and shear stress, and exactly the same problem. You see that? And they have 7 kips. So with that, and this is a single shear. What is single and double shear? Go back to lesson 1. So with the free body diagram of the bolt, we have 7 kips each. If we cut to find out the internal shear of the bolt, and that V for single shear, it V is 7 kips. So the tau, the shear stress equal to V over A, and it equal to 7 over the areas, V over A. You see that there? So that, I don't need to go back to do the same free body diagram using this knowledge in lesson 1. Now we move on to today's problem. So if you recall the worksheet 1E, if you want to check, right? If you are confused about what the concept we do here, have to recall that, go back to check that worksheet. So determine the bolt diameter. So it basically just design, create a new structure, right? So the question is determine bolt diameter. Diameters. And in this case, the design, not analysis, design. If they give you the bolt diameter and check if the bolt can bear with just 7 kips load, then it will be the analysis. So in this case, apply the general design equation. Actual less than or equal to allowable. And in this case, the shear stress, so it's about tau. So tau actual less than or equal to tau allowable. And if you see the problem worksheet 1E, I just mentioned earlier and show you the solution for the actual tau, it equal to, for the single shear, it equal to the shear force divided by the transverse areas, and that one have to be the allowable. If you recall in this worksheet, allowable equal to the failure divided by factor of safety. Failure level, factor of safety. In that case, it is about tau, so you can see that it tau failure, that tau fail to make it short, divided by the factor of safety, Fs. So from that, we can have the plug in So you have 80 greater than or equal to V time Fs divided by tau fail. And with that, if you recall, 80 equal to pi d squared over 4 have to be greater than or equal to V Fs time tau fail. So from that we can have D greater than or equal to square root of, and plug the number in, 4 times V, the shear force. For the shear force, for the single shear, it will be equal to the 7 kips. You see that V equal to 7, the applied load in that case. So go back to here, it will be 7 time factor of safety given 2.5 divided by pi divided by tau fail given 30 KSI in there, kip per second, kips per inch square, 30. So from that you will get this number equal to 0.863 inch. And in the problem 1, worksheet 2A, when we design and we stop there, minimum diameter, we stop by 2.45 inches. For this problem, it's not here yet. We make it more realistic. In the real life, you cannot go to Lowe's or Home Depot, or you order anywhere that have that the diameter of the bolt with 0.863 inches. So we need to go to the side that manufacturer normally have. In this case, they also have scenarios here. Require the bolt diameter to the nearest 1/4 of inch. 1/4 of inch. So what does that mean? As you can see, typically to the nearest 1/4 of inch. So you have, if you say the incremental is 1/4, so you have this one is somewhere between. So if you call that 0.863 inches, is somewhere greater than in terms of quarter incremental. So it will be 3/4 inches and less than 1 inches. See that? Because 3/4 inches it means 0.75. This is 0.75 inches. And the question is, go to the nearest 1/4 of inch. You cannot go back to lower. You cannot choose 3/4 inches, because that make your factor of safety will be less. You have to jump up. On-way design, you have to jump a little bit up. In this case, the nearest it will be 1. So from that, you will select your nearest 1/4 inches. 1/4 inches. In that case, so you will have the diameter equal to 1.0 inches. That's the answer. And use this concept to apply for future problem when they make it realistic. So you go out to Lowe's, Home Depots, or anywhere that you can choose. Okay, get the bowl with 1 inch diameter. You cannot say 0.863 inches, for example. So with that, we do the first part. And then the next question is, what is the actual factor of safety for this bowl that you choose? Now we already choose the bowl that 1 inches. What should be the factor of safety? And at always, as you can see, the factor of safety equation is equal to the failure level, and divide by allowable level. And in this case, we want to check what is the actual factor of safety. What is the actual factor of safety? So that we can put the allowable level equal to the failure level. The allowable level equal to the actual, because we want to say what should be the actual factor of safety. What is the actual factor of safety? So from that we can put the tau actual. What should be the actual shear stress occur in this structure after we choose the diameter is 1 inch. Okay, so that allowable, even allowable, but here we check the actual factor of safety. You replace that to the actual. So from that here, we just go ahead to plug in the number. The Fs equal to the failure is 30 KSI. Divide by the actual, it will be V over 80. V over 80. And from that, we can put the number in 30 KSI. So let's put that here, make a general equation here. So that is tau fail, and tau fail is 30 KSI, and divide by V, it will be the actual load 7 divide by 5 d square, in this case 1 square, because that you the diameter to choose. If you plug 0.862 inches in the D, then you still get the factor of safety original is 2.5, right? But now because you choose it a little bit upper, so the factor of safety, the actual factor of safety is a little bit different. So from here, with that equation plugged in, you can get 30, the bottom is 8.913 KSI. So from that, we have the actual factor of safety, in that case, actual equal to 3.37. So original, we set the factor of safety equal to 2.5. And if that factor of safety, you need the diameter is 0.863 inch. But now in the market, normally you don't get that. Round up to 1/4 inch. In this case, you choose 1 inch diameter. And because you go jump a little bit upper, so you feel more safe. And that reflects in the factor of safety greater than the original factor of safety, 3.37 inch compared to 2.5, which it makes sense. So with that, we finish the problem 2B.